Nuclear fission, a death trap awaits Tokamaks. Here is why. The theoretical basis of nuclear fission is the Standard Model, abbreviated as SM. But SM does not describe the detailed process of nuclear fission. The geometric structure of a nucleon is assumed to be spherical. The detail of the electrical interaction between nucleons do not exist. The geometric structure of atomic nuclei is assumed to be in heap. The details of the electrical interaction between atomic nuclei are non-existent, which makes this research highly risky. There is another theoretical model. Another model named Xizhidong, abbreviated as XM. XM describes the detailed process of nuclear fissions, the geometric structure of quarks, the geometric structure of nucleons, the detail of the electrical interaction between nucleons, the geometric structure of atomic nuclei, the detail of the electrical interaction between atomic nuclei, which allows us to predict a number of outcomes. Nuclear fission process according to SM. Reminder of the following element in the following slide. Structure of nucleon, electrical interaction between the quarks of a nucleon, structure of atomic nuclei, electrical interaction between the nucleons of atomic nuclei, electrical interaction between two atomic nuclei. Structure of a proton. A proton has two quarks up and one quark down. They are light by strong electroforce. Structure of a neutron. A neutron has one quark up and two quark down. Their force is strong electroforce. Interaction between quarks. The interaction between quarks is modeled as electric. The intensity of this electric force is greater than the classical Coulomb force, therefore called strong electron. This force is modeled as carried by a mediator particle called a gluon. The range of the strong interaction is about 10 powered minus 15 meter. That is about the size of a nucleon. Structure of a deuterium nuclei. deuterium has one proton and one neutron. The force is a residual electrostrong force, and the binding energy can be calculated, and the result is minus 2.22 mega electron volt. Structure of a tritium. A tritium has one proton and two neutrons. The force is a residual electrostrong force. The binding energy is minus 8.48 MeV. Structure of a helium. A helium has two protons and two neutrons. The force is a residual strong electrostrong force. Binding energy is minus 28.30 MeV. Interaction between nucleons. The interaction between nucleons is modeled as electrical. The intensity of this electric force is greater than the classical Coulomb force, therefore called residual electrostrong. This force is modeled as carried by a nuclear potential. The range of the strong interaction is about 10 power minus 15 meter. That is about the size of a nucleon. Interaction between two atomic nuclei. The interaction between two atomic nuclei is modeled as Coulomb force when the distance r is greater than Rb. Rb is the Coulomb barrier. This interaction becomes electrostrong when R is less than Rb. This interaction has a maximum value when R is equal to Rb. This Coulomb barrier is dependent on fission or fusion. The exact value of this Rb barrier is not known. The energy associated with this barrier depends on the atoms. Quantification of interactions. In SM, only the Coulomb force is quantified by the classical formula. Nuclear fusion process according to XM. The following elements of the XM model are described in the following slide. The fundamental particle of the universe, structure of neutrino, structure of quarks, structure of nucleon, electrical interaction between the quarks of a nucleon, structure of atomic nuclei, electrical interaction between the nucleons of atomic nuclei, electrical interaction between two atomic nuclei. Elementary particles. There are only two following elementary particles: the photon and the electric charge. the photon plus a photon has a rotation around its direction of travel. If it is in the right-hand direction, it will be noted as polarity plus, 中 minus. If this rotation is in the direction of the left hand, it will be noted polarity minus. The electric charge Co plus a pure electric charge of a sign plus. Co minus a pure electric charge of a sign minus. There is an energy field. The two elementary particles only have their reason for being in the energy field named Gu. Formulation of electric force. The Coulomb force is modified to the following formula. Formulation of the weighted charge. The weighted charge of an electric charge is defined by the following formula. Structure of an electron. An electron has a pure electric charge Co minus and a photon 中 minus. Structure of a positron. A positron has a pure electric charge Co plus and a photon 中 plus. Structure of a neutrino. A neutrino has an electron and a positron. They are linked by an electric force. And electron and positron are in rotation. This structure is called charge net, and a charge net can have different level of energy. So the rotation speed V can be different. And the symbol is a yin and yang symbol, just like a disk with a certain thickness. Structure of an up quark. In XM, three charge nets form a stable triangular chain. This stability is ensured by the electrical force at the three contact points of the three charge nets. In XM, this structure with the positron at the center is called up quark. This compound particle has an electric charge E plus. In XM, this positron-free structure is called a chrominate up. This compound particle is electrically neutral. Structure of a down quark. In XM, three charge nets form a stable triangular chain. This stability is ensured by the electrical force at the three contact points of the three charge nets. Here we have a chrominate with a different level compared to the previous one. with an electron at the center. This is a down quark, and without the electron, it is a down coordinate. This combined particle is electrically neutral. Structure of a neutron. Starting with the up quark called the core, the construction continues with the same principle as a quark on its three sides. We obtain a neutron. There are two down quarks and an up quark at the edge. The electrical balance is 2e minus plus 2e plus equal to 0. Representation of the neutron. The neutron has an axis of symmetry that passes through the center of the core and is parallel to the three charge nets of the core. The view along this axis can be represented by the diagram opposite. Structure of a proton. Coordinates called the core. At the center, the construction continues with the same principle as a quark on its three sides. We obtain a proton. There are two up quarks and one down quark at the edge. The electrical balance is 3 positron and 1 electron. The global charge is E plus as a positron. Representation of the proton. The proton has an axis of symmetry that passes through the center of the heart and is parallel to the three charge nets of the heart. The view along this axis can be represented by the diagram in opposite. Interaction between quarks. Interaction between the quarks of a nucleon is electric. This interaction is structural. The core of a nucleon is an up quark or a down coordinate. Each of the three quarks at the edge is built on a rib of the core. This Siamese structure makes the three quarks of the nucleon inseparable. The core of the nucleon can be thought of as a fourth quark, which allows for the following two configurations. All quarks have an electric charge, the case of the neutron. Only quarks at the edge have an electric charge, the case of the proton, which rehabilitates the fractional electric charge of quarks. Structure of a deuterium nucleus. The deuterium nucleus consists of a proton, and a neutron. Leaving aside the position in the neutron core, the distribution of electrical charges in the neutron is symmetrical to that of the proton. The E plus E minus symmetry naturally creates three electrical bonds through the Coulomb force. Structure of a tritium nucleus. The tritium nucleus consists of a proton and two neutrons. Starting with the deuterium, the second neutron is placed in the symmetry with the first. The bonds are the same as those of deuterium. Structure of a helium nucleus. The helium nucleus consists of two protons and two neutrons. Starting with the two deuterium, they are placed in parallel so that their axes are opposite. The bonds between them are in four groups of E plus E minus. Interaction between nucleons. Interaction between the nucleons of an atomic nucleus. This interaction is mainly electrical. The geometric distribution of electric charges within nucleons imposes the following two configurations. 1. Nucleons in stable bonds are coaxial. This is the case for deuterium. 2. Radial bonds are also stable if they are grouped together. This is the case for helium. 3. There is a third case which is a dynamic link. See non-standardmodel.org for details, which makes it possible to predict the behavior of a nuclear fusion. Interactions between two atomic nuclei. Interactions between two atomic nuclei. These interactions are mainly electrical. Interactions between two atomic nuclei include those between nucleons. 1. Coaxial connection. 2. Radial connections. 3. Dynamic links. These interactions depend a lot on their relative positions. For fusion to occur, the first core must position these phase charges symmetrically relative to the second core. Deuterium-tritium fusion predictions. Trap 1. Position conditions. Geometry. 3 axial faces, 3 radial faces. Probability of fusion by thermal effect very low. Trap 2. Electric force is proportional to the surrounding energy. Increasing the temperature improves the fusion, but this gain is attenuated by the increase of the repulsive electric force. To increase the probability of fusion, the pressure must be increased. There is a rise time of the electric force when the energy increases. It is necessary to use the effect of the rise time of the electric force relative to the surrounding energy. Optimal fusion conditions. Here are the optimal fusion conditions. In a cylinder with a piston similar to a four-stroke thermal engine, using the piston increases the pressure of the deuterium and tritium gas mixture. To stroke a high-energy electric spark in the gas, to strike a high-energy electric spark in the gas, high pressure and high temperature will thus be obtained. The fusion rate is maximal for a short time because the surrounding energy increases rapidly by spark. The repulsive electric force remains at the old value, therefore weaker than that of the future. High pressure keeps atomic nuclei close together. The nuclei are constantly changing position, which promotes fusion. Evacuate the content of the cylinder, then readmit the low-energy mixture. Useful links for more details. https nonstandardmodel.org http jack.dong.3.3.fr.
Hi, my name is Jacques Dong. I'm an electronics engineer. I have a passion for fundamental particles. Outside of my professional life, I've devoted a lot of time to studying them. The result can be found on the website nonstandardmodel.org. They are very different from the standard model.